Indeed, I'm very excited about this evening's lecture, not only because our guest speaker works at NASA and drives a rover on another planet, not only because our chairman is a famous scientific journalist and honorary fellow of the RSC. I'm very excited because this event allows us to celebrate a great scientific enterprise. Paolo and his colleagues at NASA have landed an incredible machine on Mars and are now operating it to do great scientific experiments. But that machine was built on this planet, and its instruments are testimony to cutting-edge scientific work that was carried out years before the mission was launched. I'm very proud to show you one of the RSC journals, the Journal of Analytical Atomic Spectrometry, where in 2007 scientists published an article about ChemCam, one of the chemistry instruments now on board Curiosity on Mars. Today's lecture is a celebration of the work of many scientists, those who worked for years to develop the science and the technology to make this mission possible, and those who work on it now. I'm now very happy to introduce our chairman, Quinton Cooper, who, as I said before, is an honorary fellow of the Royal Society of Chemistry. Quinton went to school in Grimsby before heading north of the border for a BSc in psychology and perhaps most appropriately ahead of tonight's lecture, artificial intelligence, at the University of Edinburgh. His journalistic tendencies were then exercised at the University College Cardiff, where he obtained a postgraduate diploma in journalism studies. He started his career at the BBC in news and current affairs, then produced youth programmes at Radio Scotland before moving to Radio 5 in Manchester, creating programmes such as the fantastic Hit the North and Bite the Wax, presented by the then unknown Armando Iannucci, and for now writing and producing I'm Alan Partridge and The Thick of It, etc. After moving to London, he produced a number of arts programmes before becoming one of the regular presenters of Kaleidoscope. And while it has more than once been rather unkindly observed that he has a face for radio, he is a frequent television interviewee and has presented the series Science Fix for BBC 4 and New Scientist Reports for Discovery Channel. Most famously, he has presented Material World on Radio 4 since 1999, a programme described by author Bill Bryson as quite the best thing on radio. So now, Quinton, over to you to introduce tonight's event. Thank you.
Thank you, Robert. Thank you, it's an honour to be here. The only trouble with that introduction is I now am sneakily hoping for a fire alarm where we have to go back through the Geological Society and travel back through time to escape a fire, but I'm actually hoping that doesn't happen. There's a line that came to my mind when introducing tonight's guest. It is good to renew one's wonder. Space travel has again made children of us all. It seems to me a perfect encapsulation, the sense of wonder, enthusiasm, passion, insight that the Mars Science Laboratory and Curiosity has evoked and inspired in a whole range of them. I remember being at the moment, August the 6th last year, when it was very nervily touching down on Mars. I was with a group of about 200 people at the Natural History Museum at 6 o'clock in the morning, nervously watching a live feed from NASA. And it's a long time since I can remember a space mission engendering that level of excitement. That was before we'd even started to find anything. What makes that line, though, it's good to renew one's wonder, what makes that line particularly impressive for me, though, it was written over 60 years ago, before even our first sputtering Sputnik was spat out into space. And it's all the more appropriate because it comes from the Martian Chronicles, a collection of stories by the late, great Ray Bradbury, in whose honour the site where Curiosity landed 8 months ago was named. Now, the man we're about to hear from helped choose that site, and he continues to help make children of us all. In his own words, he's team lead for ingress, egress, and operations inside Victoria Crater, and among other things, quote, responsible for the evaluation and analysis of the daily mobility data. But I prefer to think of him as someone who goes to work on Mars every day. Please welcome to the RSC, Paolo Bellutta. It's important, especially when you're dealing with somebody from NASA, to have very clear mission objectives. So, The very rough plan is that Paolo is going to talk for about 45 minutes. Yep. He's got a bit of a cough, so we'll see how long his voice holds out, right? After which, I'm going to throw it open for your points and questions here, your points and questions on the upper level, and I don't know which way to point, but for those watching the webcast, your points and questions out there as well. As Robert said, the hashtag is RSC Public Lectures, and first you must follow at RSC_comms, comms with 2 M's. Are we all clear? And Paolo, like Curiosity Rover itself, we are in your hands. Thank you.
So let's get to work. I apologize in advance. Not only had to put up with my really bad accent, but also with a really low voice. I work at the Jet Propulsion Lab for the past 14 years. The Jet Propulsion Lab is one of the 12 NASA centers, and what we do is to develop robotic missions to explore the solar system. Most, I would say 90–95% of the images that you have seen of the planets, they come from missions that we have developed and managed. The remaining 5 is probably Hubble. So you're saying, well, if you work for NASA and you drive a rover, why are you here? Well, that is a really good question. So the blue thing here, the blue dot, is Earth. The red dot is Mars. The yellow thing in the middle is something that we call Sun. In spite of the really powerful NASA resources, we haven't developed a system to transmit signals, radio signals through the Sun. So for the entire month of April, we cannot communicate with Mars. So all of the missions that are on Mars or around Mars, they are in not standby, but in sort of a reduced volume of data acquisition. I don't know how many of you are familiar with Mars. Mars to me is like a second home, but I listed a few things that worry me. The remaining things are a problem of the geologists. Mars, the diameter of Mars is about 1/2 of the Earth, but the surface that you need to explore is equivalent to the surface of Earth. So there is a lot of things to look around. So far, we have been exploring only an area that is around the equator with rovers, and with landers a little bit more north. We had Phoenix, we had Viking landers way before then. I still remember the black and white pictures on my TV set. I never thought that I was going to look at those pictures for a living. The gravity field on Mars is about 1/3. That means that when we need to make experiments here on Earth, it is kind of difficult. There are means to replicate lower gravity fields. They make use of parabolic flights, and therefore you can have a lower reduced gravity only for about 30 seconds or so. So that is definitely not something that we can do for testing rovers. The other thing is there is an atmosphere. It's not air, it's not breathable. If you breathe it, you probably die. But the issue is that it is thin. It is so thin that you cannot cool devices with a fan. But the major problem is that it is thick enough that you have to deal with it when landing a rover or anything to Mars. The planet doesn't have a magnetic field, and besides that, you cannot use a compass. There is no radiation shielding from the magnetic field. Therefore, all the electronics that you send to Mars, they need to be protected against radiation. It is really, really, really cold on Mars. A torrid summer day on Mars is about freezing. and during the night and in winter time can get down to -90. So it is pretty cold. That means that we need to warm the vehicle in order to keep it alive and in order to make it work. Especially all the gears, all the motors, they need to be warmed up. The atmosphere is really thin, but winds on Mars can be really fast. We have measured up to 400 kilometers per hour, but the atmosphere being really thin, this is equivalent to a nice breeze on Earth. So our vehicles, they don't fly away. The Martian day is about 39 minutes longer than Earth's. And therefore, it makes it an interesting way of handling the mission. I have a slide on that. The Martian year is about 2 years. And that's one of the reasons why we can send missions to Mars only about every 2 years. About every 2 years, Earth and Mars are closest, and therefore, to reduce the amount of time that it takes to get a mission to Mars, that's when we do it. Let's get this, and let's get to the juicy stuff. This is not a small vehicle at all. It is about 3 meters by 3 meters in footprint. Is about 2.5 meters tall and has lots of cameras. There are 2 color cameras, one here, one here. One is about 30 degrees field of view. It's a color camera, 1600 by 1200 pixels. The other, same resolution, but has optics only 5 degrees. Therefore, we can get more detail further away. We have another camera about here on the turret connected to the robotics arm that can be pointed in any direction and moved around and can take pictures from 2 centimeters distance up to infinity. And that's what we have been using to take pictures, for example, of the belly of the rover, pictures of the sand and rock samples that we have seen. We have cameras in the front, wide-angle lens that are used to take pictures of the terrain so that the vehicle can understand whether there is an obstacle or not. We have more cameras near the turret, 45 degrees field of view, monochrome cameras that are used to take pictures of the terrain surrounding the vehicle to decide in which direction to move. Sorry. Now let's get to the really juicy stuff. We have some instruments that measure the environment of Mars. We have Dan that measures the subsurface hydrogen. We have REMS from Spain that measures the weather, direction and speed of winds, temperature, relative humidity. We have RAD from the Russians that measure the radiation level to understand whether the current environment of Mars is livable by an astronaut. And then we have SAM and ChemIn, which are the 2 chemistry labs that we have inside the vehicle. SAM is a mass spectrometer and measures the chemistry of the samples, and ChemIn, the mineralogy. How do we get the samples? If it is a rock, we use a drill that is not too different that you can buy from a hardware store. It is kind of more expensive. We have drilled the samples down to about 5 to 6 centimeters of depth, about 18 millimeters in width. Sorry to confuse units of measure. We have a scoop that now we can use to thick sand sample. Either the drill sample or the scoop can be sieved. Forgot to say that the drill is a percussion drill, so it pulverizes the rock, and the dust that is recovered can be sieved. We recover only the small particles, about 150 microns in diameter. Mars is covered by dust. Nobody has done any dusting in millions of years, so we have sent a $2.5 billion machine to do brushing. Getting back to serious stuff, when we want to use the alpha particle X-ray spectrometer, which is sensitive to the surface dust, we want to remove it and get the actual composition of the rock that we are analyzing. This is the location. This is a map of Mars. The northern hemisphere is pretty flat and boring. The southern hemisphere is all bumpy. This is Valles Marineris. Is a really deep canyon. Here we have Olympus Mons, a giant volcano that is no longer working. Here is where Opportunity is, and she's still working. This is where Spirit is, and my friend on Mars has stopped talking to me about 3 years ago. This is Gale Crater, where we have landed Curiosity. Why did we go to Gale Crater? Gale Crater is a crater that is 120 kilometers in diameter. When I deal with big numbers, and to me big numbers means more than 2, I have trouble understanding what it means, so I overlaid a Gale Crater on something that I'm pretty familiar. This is the Los Angeles area where I live and where the lab is. The lab is, let's see, the lab is more or less here, and I live really close by. But I wanted to give you a better sense. That picture is just this tiny area, the area that we are going to explore. So I overlaid, I tried to do my best to preserve the scale. This is London, and this is that area. So it is a big area to explore, even for a big rover. So why did we go to Gale Crater? In the middle of Gale Crater, there is a 5,000-meter mountain. And this mountain has layered bedrock, exposed layered bedrock. And geologists, I hope that there are no geologists sitting here. There are funny people. They like rocks. I like cheese. They like rocks. But I understand why they like this structure, because layered bedrock shows you the evolution of the planet. Lower layers, they tell you what the environment was on Mars in ancient times. Higher layers, they tell you more recent times what was the environment of Mars. So we have exposed layered bedrock for thousands and thousands of years. Well, already they work on millions of years. I also wanted to give you a sense of the size of the vehicles that we have sent on Mars. This is a copy of a Sojourner. This landed on Mars in 1997. I was not at the lab at the moment. This is a copy of Spirit and Opportunity. I have driven both. And this is Curiosity, the guy in the middle. That's me. I'm pretty short, but just for size. Also, here you see a comparison between the wheels. So we doubled the size of wheels on each mission. And also, I wanted to give you a sense of the computing power that we have on each vehicle. Curiosity, although has a really powerful computer on board, it is equivalent to a really old iMac. One of the questions that I get asked all the time, and it's really difficult to answer just in words, is how do you deal with a mission on Mars, especially since the day on Mars is longer than Earth's. So I was saying that a day on Mars, which is called Sol, is about 39 minutes longer. What we do is to, and the time that it takes to send commands from Earth to Mars depends on the distance between the two planets. At the moment, is about 20 minutes. It would be 20 minutes if we could send commands through the sun. So we send the commands from Earth to Mars in early morning for the vehicle, early morning for a teenager, so about 11 or 12. The vehicle executes the commands that we send during the day. The reason is that during daytime flight, it is warmer, so you need to spend less energy warming up the vehicle. And then in late afternoon, around 4 or 5 in the afternoon, it sends back the results for that chunk of activity. We receive the telemetry, and we prepare the activity for the following sol. So we work the Martian nighttime. Being the day on Mars being longer, the Martian nighttime shifts. So at one time, I was going to work at 8 in the morning, the next day at 8:20, sorry, 8:40, 9:20, and so on and so forth, until my day was beginning at 2 a.m. That is really nice. There is no traffic in LA. There is no problem parking. Finding a restaurant open at that time was a little bit of a challenge, but that is not the issue here. So for the first 90 sols, that's what we did. We worked during the nighttime for Mars, and we worked weird hours. Now we have switched working Earth time. That is, we begin our workday at 8:15 in the morning, and we go on, let's say, 6 or 7 in the afternoon. When I left, we were working 6 days a week, but we worked 7 days a week up to January. And when I go to fly back to Pasadena, I'm going to work just 5 days a week. So how do we drive our Rover? Being the US, there is absolutely no way that we can do anything without meetings, PowerPoint presentations, and boring stuff like that. So, but in this case, it is pretty obvious. Since we need to prepare the activity for an entire Martian day, what we do is to look at the resources that we have available on that day, and the resources are mostly time, the amount of time that we have to do any activity, the amount of energy that we have available, the amount of disk space that we have available on the vehicle, and the amount of data that we can downlink from Mars on that. Given the resources that we have available, we just decide what science observations we can do with those resources. So geologists, they have sort of like a battle. It's not a really bloody battle, at least it hasn't been so far. And we try to find the best compromise on the activities that we want to do. We, specifically we drivers, what we do is to take pictures at the end of every drive. These are 3D pictures, so we can look at them from different perspectives. We can place the vehicle on the surface and see what is the vehicle attitude position, and see if the obstacles that we have on Mars would be a problem for the vehicle. And we can simulate commands. Let's say if I'm going to tell the vehicle from this position move forward 10 meters, that's what the vehicle is going to do. These pictures, of course, are relative to Spirit and Opportunity. Actually, this is Opportunity, but we can do the same on Curiosity. We can look at the simulation from different point of view, and we can compare the daily activity to what was planned. That is the easy part. The hardest part of my job is being a pessimist. That is, I try to imagine all the possible things that can go wrong on Mars. These are pictures that have been taken by Spirit and Opportunity. This one as well. This has been photoshopped in simply to give you a sense of size. So there are pretty obvious obstacles and hazards. Here you have a really steep slope. Here you have a drop. But there are some hazards that might not be really obvious. So I'm going to show you some of them. For example, here we have a very thin layer of sand on top of bedrock. In that case, sand is going to act as a lubricant on bedrock. So if you place the wheels on that, your vehicle is going to slide off, and you need to find another job. Here we have driven the vehicle between two craters that were filled by sand. Sand can be a really good surface to drive on if it is really well compacted. But if it is windblown sand, typically is made of really fine particles. And these fine particles might get your vehicle trapped, and therefore it is quite hazardous. So that's why we didn't just drive straight through. But so we drove between these two, and there is not much space left. So if something happened at that location, it would have been a problem because you don't have enough room to maneuver. So what we do is to use the vehicle itself. And the rover has an instrument called the Inertial Measurement Unit, which is equivalent to your sense of equilibrium. And it tells you whether the vehicle is going uphill, downhill, on a slope. And we can set limits and we can tell the vehicle, you're supposed to drive on flat terrain, but if you start driving uphill, stop. Or if you're driving downhill, stop. We can do the same by monitoring the position of the wheels. If, again, we are driving on supposedly flat terrain and one of the wheels is moving up, we know that that wheel is trying to go over a rock or an obstacle that we didn't see. And we can say to the vehicle, stop. We can do that. We can use this driving modality that we call blind driving, because we are the eyes for the rover. The rover drives blindly. It doesn't use the cameras. We can say to the vehicle, you're here, go there. I don't really care what route you take. Just avoid all the obstacles that are between here and there. You have 1 hour to do. In order to do that, the vehicle needs to know where the vehicle is and where the goal location is. The vehicle measures its own position by counting the wheel rotations and the direction of motion. If the wheels, though, they slip on terrain, especially going uphill, for example, then the position that the vehicle has is wrong. We use a third mode called visual odometry, which is a really big word to do what we normally do. We don't count our steps while moving to determine when to turn. We look at the objects that are surrounding us and look at the distance between us and those objects to know where we are. Visual odometry does the same thing, but with a computer. Takes a picture, tries to find objects in these pictures, takes a step, takes another picture, and tries to find the same objects that are visible from the previous picture, and computes what is the distance of those objects. From these, we can compute the real motion of the vehicle. This is a picture of the simulations tool that we have on MSL. They are more capable, and driving on Curiosity is much easier than driving on Spirit and Opportunity, but still is quite a challenge. So one question that you might have is, if you have autonomous driving and you have visual odometry, why don't you use it all the time? That's because the top speed of our vehicle is 150 meters per hour. But we can drive slow. So driving with visual odometry or driving with I don't know, we do about 40 meters in an hour. When we use both, we drive so fast that we can do 25 meters in an hour. So whenever we can, we try to use flight mode. One of the things that I was asked in 2008 is to analyze the potential landing sites in terms of reversibility. That is, suppose that you have safely landed on Mars. I want you to tell me if from that location you can reach the science goal. So George has proposed, I think, 50 possible landing sites. We pared down to 4 possible landing sites, and 3 of them had the major science goals outside the landing tips. So it was really important to make a determination if those 3 landing sites had science goals that were reachable. Reachable not only you can do it in 10 years, but also do it within the time allotted, which is 2 Earth years, and within the given maximum distance, which is 22 kilometers. We didn't have any information about the surface because we didn't have any vehicles at those locations. But we had this wonderful camera. The high-rise camera is a telescope. It's a half-meter telescope pointed to Mars, and it gives you images that are really, really detailed. If that camera was pointed at Earth, those images would be classified top secret, so you wouldn't see them. While you can go on HiRISE website and download them and look at them. They're beautiful. Just to give you, well, to me, they're beautiful. I digress. So this is one of the first pictures that HiRISE took. This is the rover Opportunity. You can see the rover, you can see the shadow, you can see the mast with the cameras, shadow of the mast. And if you can pay attention pretty closely, you can also see the tracks left by the vehicle. This is from about 200 kilometers up. So using this camera, I managed to extract some products that are necessary to compute whether you can drive and how fast, how slow you can drive on Mars. From the images, we can compute the slope of the terrain. We can compute the type of surface, the type of terrain that we have on Mars. Clearly, driving on sand or on sand dunes is different than driving on bedrock. We can also locate rocks on Mars from orbit. I have a map of about 4 million rocks on Mars. Not rocks, rocks. So this is one of these maps. Let me zoom in on this. This is an area that it is wind-blown sand. So if it is really compacted, it could be a good surface to drive on. If it is small particles, uniform size, it is really nasty stuff and you want to stay away from. These things is black and white lines. These are sand dunes, probably tall like this room. So it's kind of difficult to traverse them. So these are the type of terrains that we have to deal with. These are some of the maps that I have created. Among the various things that I was able to do is to automatically compute where we have rover trams. That is locations that you can drive around, but if you want to get out, you can't. Typical example, this crater is about 2.2 kilometers in diameter. You can definitely drive around in that area, but it's kind of boring. After a while, you get bored. The same thing here on the mountain. There are locations that you can drive around on, but you cannot get off. Once you have these traversability maps, you can use other algorithms that allow you to compute the optimal path between one location and another, and therefore minimize the time that it's going to take you to go from one place to another. This before even planning. Of course, my bosses really didn't trust me. They wanted to test what I had done. So we did sort of like a game. And so we decided we took one image of the difficult image. And we decided on a set of starting locations, a set of end locations, and some intermediate points to drive to. And I was there with my computer using my system. And on the other side, I had a group of 6 planetary geologists that are experts in trying to understand where you can drive on Mars. And we compared the results. I got this map in a couple of hours. The geologists had a similar map after about a month. So in the meantime, I had to kill time somehow. So I did things like find the shortest path or the longest path, how long it was going to take to drive between these points. Now I'm going to tell you a couple of things that I find amazing about the landing event. Things that they were not really well publicized, but I find it really, really great. While Curiosity landed, she had a pre-programmed list of events, when to do certain things and when to do the following things. When she was transitioning from one activity to the next one, she was sending out a signal that was too weak to be received directly on Earth. And therefore, we used the two orbiters that we have, the Mars Odyssey and the Mars Reconnaissance Orbiter. We also asked the European Space Agency to position carefully Mars Express, but we had to rely upon our assets to do the relay. So while landing, we had to position the two orbiters carefully. We had to position the two orbiters above Gale Crater while Curiosity was going to land. The only thing that we could do is to change the orbit a little bit, just a tiny bit. And we had to position those within 30 seconds. So within 30 seconds, they needed to be there. An orbiter is different from a rover. You cannot just say to an orbiter, you sit there and wait. It falls to the ground. So, so this is amazing. So I try to find an equivalent. So it's like having a car leaving Maine, driving to Los Angeles, while another car is leaving Yellowknife and driving to LA, while a third car leaves Anchorage, Alaska to LA. And they all arrive at Hollywood and why within 30 seconds. The second thing that I found really amazing about the landing is something that didn't attract the media attention. The media attention was on the last 15 seconds of the skyscraper. Yeah, it looks crazy, but we haven't done crazy things. The really innovative part of the landing for Curiosity is way back at the beginning. As I was saying at the beginning of my lecture, you have an atmosphere on Mars that you have to deal with. And typically we put a heat shield in front of the vehicle that now you want to land. And the heat shield is used only to slow down the vehicle. On Curiosity, we did something slightly different. Instead of having the heat shield being kept perpendicular to the path, the landing path, we released two masses from the back of the vehicle, which from the bottom part of the vehicle, and therefore that part became lighter and positioned that way. So instead of flying perpendicular, we came down at an angle. And therefore we managed to use the heat shield not just as a brake, but also as a wing. So we flew down. We also installed small pockets in the back, directed so that we could turn the vehicle in that phase. So when it was turning to the left, it was moving to the left. Turning to the right, it was moving to the right. And therefore, we managed to fly and control the descent. Why that is important? Because even a minor change in temperature or pressure of the atmosphere at the higher levels means that your vehicle is going to land in a very different position than you intend to. The vehicles up to that point had a landing ellipse of about 100 kilometers by 30 kilometers. Curiosity instead had a landing ellipse of 21 kilometers by 7. So it was a dramatic improvement in precision landing. Why is that important? It is difficult to find a parking lot that is 100 kilometers by 30 on Mars. In London, it's impossible. But it is much easier to find a flat spot that doesn't have many obstacles on Mars, very smaller. So you have many more options available to you. I'm done boring you to death, so I'm going to show you some pictures that I love. This is the third picture that Curiosity captured. This is the mountain, the 5-kilometer mountain, Mount Chubb. This is the shadow of the rover. We landed in late afternoon for the vehicle. While all my colleagues, they were joyful and that Curiosity had landed, we still had a job. I started looking at my maps, and the few of my hair left on my head were standing like this because this is an area that is just north of where we landed. Enhancing contrast a little bit, that's what you see. For example, had the vehicle landed here, this is a 50-meter drop-off. If you're not scared, there is an 800-meter crater. And those black dots, those are rocks. Again, not frogs, rocks. This is a high-res image projected on the elevation map that we have. This is the valley that we are going to probably drive in about a year and a half. This is the exposed bedrock that we see. Another view of the same valley. These are really big dunes that we probably have to deal with. This is another view of the same valley. The difference in height between this spot and the bottom is about 200 meters. This is another simulated view of the same valley. This is the vehicle to compare size. This is another view. If you can't see the vehicle, that is the vehicle. This is not a simulated view. This is an actual view. This is one of the mass cam images that we have collected. This dark lake is not a lake. It is basaltic sand that has accumulated there. And you can definitely see the bedrock in the background. This is a view of Mount Chubb. This is the valley that we probably are going to drive on in about a year and a half. This is a view of the same area from a different vantage point. And that tiny thing, that is a tiny rock of the size of a vehicle. Chiara, this is the image I've given you. This is a view taken on Sol 44 by Curiosity that I love. I like taking pictures. I'm not really that good at taking pictures, but I like it because it has the tracks. Has the sun. This was taken in late afternoon. We have the sun shining onto the dust particles in the atmosphere. This is the last panoramic picture that was taken before going to Solar Conjunction. This is Mount Chubb. This is the colors that you will see if you were on Mars. This is a picture where we have stretched the color, stretched the contrast, and somebody that didn't have a better idea pictured the sky on Mars blue. The sky on Mars is not blue, it's orange, more or less the same color that the sky is in LA. But it is, yeah, really, the first time that I saw pictures from Mars, I said, oh, this just looks like LA. the sky on Mars, it doesn't get blue until sunset. Thank you.
Paolo, thank you. Lots of curiosity, lots of wonder. A couple of questions from me, and then I'm going to open it up because I think there'll be plenty. It struck me that actually Robert gave a much more detailed introduction of me at the start than I did of you. And there might be people like myself wondering, what on earth is the career path to end up as a Mars rover driver?
I think that before that, in order to encourage especially young people to ask questions, I have presents for you. I think that the most important aspect of my job is that I have solved many different problems, not only on Mars, but even on Earth. Really weird problems like finding the best structure for a chocolate. Yeah, I have done many weird jobs in my past life. But since there is no book on how to drive Mars, on how to explore Mars, we are basically being pioneers. And therefore, it is important to have ingenuity and to come up with really weird solutions. We really try to come up with different methods to solve really uncommon problems.
Did you start off as a physicist, an engineer? I mean, what was the route?
I started as a physicist and then moved out to computer science. But I think that it is mostly my career that brought me to being on Mars. I didn't even dream of being at JPL. In fact, when I met what was going to become my future boss, I told him, well, I don't know if you're going to hire me, but you made my day visiting the lab today. So I don't know if it was the right thing to say, but yes.
And you talked about a couple of areas that they could have gone. You made a joke about how, if we went there, it would actually get very bored. But I wonder what is it actually like when we're 8 months into the mission. What's a normal day like? Is there a slight element of okay, here we go again, or is every day exciting?
Oh yeah. I was saying that 80 or 90% of my job is boring, but the 10 or 20% that is remaining makes up for it big time. But one of the reasons why I'm here is that after doing this for 9 years, it starts, even that 10% starts to become routine. So having interaction with the public, it helps me. This is my 19th lecture in 3 weeks. So I have seen many people from 4.5 years old children to up to you. So it helps me charging the batteries.
We should say most of those lectures, if not all of them, were in Italian.
A few of them were in English.
Oh, a few of them in English as well.
Yes.
One more question. Shall we get you back out from behind that?
Yes.
Because I don't think you need to be. You may as well be front and centre. Like you said, he has gifts for people asking questions, which I'm exempted from. Otherwise, I'd just be taking. No. Oh, great, fantastic, thank you. You're not the only Curiosity driver.
I'm not.
So is it competitive? Do you go for, fastest speed, longest distances?
No. I wouldn't say that there was a battle to get hired, but it was a decent selection. There was 16 of us when we landed, and then 2 left. Apparently, Google is better. On Opportunity, there is 5 of us. There is 2 people, including me, that are in common between Curiosity and Opportunity.
And do you know who holds records? Do you know who's done the most hours? Do you know who's got the rover up to the highest speed and all that sort of thing? Who's done the steepest incline, whatever it might be?
Yes, I'm the second in line. There is only one person on Earth that has driven farthest on Mars than myself.
Right. Are you gaining?
He is one of the people that moved to Google.
You must have been so happy. Okay, I have other questions, plenty of them, but I think it's more important we take yours. We're also going to be seeing if there's anybody coming in by Twitter as well. There's a hand up there. Now, what we're going to ask is, because this is being webcast, when the microphone comes to you, as it surely will, hold it close and be clear. Thank you. Gentleman there.
Autonomous driving. What is the problem with...
Just a little bit lower, sorry. It's going to distort.
What is the problem with making autonomous driving faster and more reliable?
I would say the processing of the images at the moment is the limiting factor. But even just to give you an idea, it takes about 10 to 20 seconds just to capture the images.
They're beginning to get the idea now. The hands are going up. We'll go to the back there, because I want to make sure we play the whole room. We'll come back to you, don't worry.
How is the signal processed from the station at Mars to get such clarity on Earth? I mean, what is the method?
We take pictures, and depending on the volume of data that we can downlink, we can select, we can pre-select or change our mind later on the compression level for the images. We can reduce the detail of the images, and therefore it takes less volume and less time to downlink. If we like a specific picture, we can retake it at a higher resolution later on. Yes?
Hang on, can we get the microphone back to you then as well? Sorry.
The signal from Mars starts as a minute power level. Now, after so many millions of miles, I mean, it's lost in noise somewhere. So what is the method to recover that among all the peripheral noise?
Okay, the signal gets sent from the rover to one of the orbiters, typically. The orbiters have an antenna that is about 3 to 4 meters in diameter. And on Earth, we have the smallest of antennas that we use is about 34 meters, but we can use larger ones up to 7 meters. They're cryogenically cooled. So even if the signal is really, really weak, as you're saying, we can recover the signal.
Okay, we're going to go to the one back, and we're going to come back to the front. Don't worry, you won't be discriminated against. And yes, you're right about millions. I think Mars is as close as about 35 million miles furthest away, about 250 million, isn't it? So it's a big distance.
Has there been water discovered on Mars? Okay. Has there been water discovered on Mars?
We haven't discovered detected that. I'm not being a lawyer, but we have discovered water ice on Mars. Phoenix mission that landed at about 60th parallel found water ice. We also have found rocks that have been formed in presence of liquid water. At the moment, liquid water cannot be present on Mars. The pressure is so low that you're close to the triple point. So if you put a glass of water on Mars, it will evaporate.
Paolo, can I get you to come? We'll get you to stay at the front for the benefit of people's necks, but I was just enjoying a little bit of mobility there, like the Curiosity rover itself. We're going to go to these two gentlemen at the front here who've had their hands up for a long time.
Any news on the 2020 MSL, the new instruments, or any ideas of what it will be like or different to the current MSL 2020?
MSL, the 2020 mission, or we call it the hindsight mission, is still in the definition phase. So they're still debating what instruments to put on that mission. I don't.
Okay, and just immediately behind.
I've recently spent some time in the interior of Mars. There wasn't much evidence of life there. How much discussion was there regarding the landing sites, regarding geography and evidence of life when you chosen the landing spot?
Mostly it was due to the geology that we would find each landing site. For the part that I could understand, I attended those landing site selection meetings and the geology part. I would say that besides doctors, MDs, geologists have the weirdest link up that I could find.
So biologists lost.
Yeah. So I'm.
Okay, we're going to go to, there's one up there, which is going to be an interesting challenge.
Just a shout.
We've got to play the whole road. I think we might just have to, yeah, and I'll try and relay it for the benefit of the people watching the webcast.
We were talking about the hindsight.
Yes.
Could you consider having a UAV, given the progress that's being made in unmanned aerial vehicles? Flying a rover rather than a driving rover.
Okay, so would you consider a flyover rather than a roll-over mission?
So there have been studies trying to develop a flying vehicle for Mars, specifically a blimp, an aircraft. But the atmosphere is really, really light, so it's not easy to fly on Mars. The other thing is that having the really strong winds makes it really difficult to control where you go. So among the various other things that I've thought of is to just have a balloon on the surface and be moved up. We also have found these were developed and studied way before Spirit and Opportunity. We have found that at the end of the summer, Martian summer, we have really strong winds, and those help cleaning the solar panels for Spirit and Opportunity, but beyond that season of high winds, we don't have much wind at all.
Are you confident that any future Mars missions, for at least a while, you'll be involved in? Is Mars now the rest of your working life?
I hope to get to my retirement age driving rovers.
Right. Now we've got a couple of questions. I'll get you to read them out if you put a microphone in front of you. We've got a couple of questions that have come in via the wonder of Twitter.
Yeah. So how much damage does Curiosity suffer from the recent solar flare, ionic storm, and normal sandstorm?
Sandstorms, they are not really a major problem for Curiosity, because the only thing that does for that vehicle is to reduce the range of the temperatures. So the maximum temperature lowers, but the lower temperature rises a little bit. It acts like a blanket. Also, it makes the atmosphere a little bit dusty. So it reduces the quality of the images that we can see. So I teach up a portion of the question. Related to the solar flare. We don't know exactly what happened on Sol 200, but the symptom is that one of the banks of flash storage, which is not too different from USB sticks that we use every day, again, a little bit more expensive, it stopped working. And so for the moment, we have a curtailed that area, and we don't plan to use it. We tried to repair it, and it didn't work. It is possible that that was related to radiation, because more or less on the same day, Opportunity had a similar event without permanent damage, actually. But the so far we had permanent damage on the 8th.
Is it factors like this that led to you moving from a 7-day week to a 6-day week to a 5-day week, or is it more just that after the initial excitement, nobody wants to work on it 7 days a week? Money. hope you got it on the webcast and to find
Yes.
mine for money there, but yes. So that's simply it. Because obviously some people think you've got this incredibly expensive kit and it's incredibly hard to get to place. Why on earth aren't you getting every second use of it?
I would say that all these reductions going from Mars time to Earth time, going from 7 days a week to 5 days a week is a cost reduction. It is, of course, kind of expensive to manage this mission.
Okay, we're going to go to back again. Yes, and there.
What's the expected life expectancy of the vehicle?
Paolo, come back, Paolo. Come back.
Okay. The life expectancy is about 2 years. And, but my hope is that it is going to last much more than that. Opportunity was designed to last only 90 days, and she lasted more than 9 years. So my hope is that, as I was saying, I get to retire before giving up driving. Maybe my children.
This is a good point to point out that there are clearly sheets. You've just because you hope she. Why are they sheets?
Well, it's been an opportunity in spaceships. They are female for that reason. There is a contention between drivers whether Curiosity is he or she, in spite of being a nuclear-powered vehicle with a 10 megawatt laser. To me, it's still a she.
I thought that was a convincing argument for it being a she myself. And then we'll come to you.
What are the key mission objectives?
Trying to find organic compounds. Not to find life directly, but compounds that would necessary for life.
So the precursors.
That is
Would it have actually been problematic were it to find life? Are we not psychologically ready for that?
I don't know. I get asked quite often whether we have found life on Mars, and my answer is no, not yet, because definitely if we had found life on Mars, there would be lots and lots of people involved. So I haven't seen any here so far.
You're not implying when you have a lot of beer you tend to find life on Mars. It's the other way around.
Well,
I just want to get cause and effect sorted here.
Yes, we don't have any instruments on board that will be able to detect microscopic life. Clearly, what we say is, if you see a dinosaur bone on Mars, stop. But so microscopic life forms we will be able to see. I don't know what type of measurements we will be able to make those life forms. But yeah, the main objective is just to find compounds. Okay.
I suppose I'm being mischievous and just wondering, would it have taken up all that much extra space to have also had something that tested for that there? I just wondered if they deliberately left it off because maybe as a species, it's a bit of a psychological jaunt.
The problem is that you had to define light, and then you had to make sure that the instrument you're going to put on the vehicle can detect those, and then you had to make it able to survive on Mars. So it is not easy.
Gentleman there, you've been waiting a while.
Being a driver, have you actually touched Curiosity? And if so, is there a bit of you on Mars?
They don't let anyone touch Curiosity. Being an asset that lands on another planet, we need to make sure that everything is sterilized. The only part that was not sterilized that went that way was the third stage, and that was used to leave Earth's orbit. So what we did is to, instead of pointing to Mars, we pointed 20 or 30,000 miles. So that after separation, we corrected the trajectory only of the land. And that one. So no one has touched.
Sticking with the driving though, most drivers, when they get a new vehicle, they take a while to get the measure of it. There's a few little, bad gear changes and things. Did you have that with this?
Well, yeah. So we have two vehicles on at JBL that I can use to do some testing, and I wanted to test what happens when you go up and down like this tall, and that didn't go very well.
Upside down, not very well, or
No. But the one of the mechanisms had a minor.
The hands here, go here first, and then there.
Thank you for coming. It's a real pleasure to listen to you speak. Because you're a driver of the rovers, I've got a question that's very specific to that. I know that if I was driving Spirit when I got stuck in the sand trap, I think I would still be hiding under a rock. What was all that like? Was the mood like? How's that person recovered?
I was one of the Spirit drivers, and it is still a painful experience. I go to try to be as brief as possible. We needed to move the vehicle to specific location to survive winter. There were 3 routes that we could take. We tried the first one, it didn't work. We tried the second one, it didn't work. Well, we were on the third and last one that we knew it was hard and more difficult to drive on. Also, during the first 2 attempts, we ate up some of the time that we had available. So we had our tail on fire to get to a specific location. You have to keep in mind that the Spirit had one stuck wheel on the right front. So controlling the path of the vehicle is really difficult. On Sol 1871, there are some numbers that are in my head. This is one of them. We had only limited amount of data that we could capture to do that driving. Had only one image, really low quality image. Even if we had more, even if the quality of the images is better, we would not have seen that next to the area where we planned to drive was an 8-meter crater. The vehicle, instead of following the path we had assigned, moved away about like this much, and the left side of the vehicle that crater. And we had trouble getting out. I helped in creating a simulant for that type of soil. We shoveled 5,400 pounds of dust in the summer. We tried once to find a movement that would get out the vehicle unstuck. On the last few days, we were and we came up with the craziest possible ideas. And so we said, well, moving wheels backwards, forwards, in any direction, it doesn't help. We move the vehicle only a couple of seconds. So we said, well, let's just steer the wheels and use the wheels sort of like a swimming method. And in one day, we moved this much. Unfortunately, a week later, we ran out of energy. So to me, we ran out of time. We didn't run out of methods. but it's still big.
That did sound incredibly raw. I mean, now you sound like you're through the process, but was there a lot of time when you were beating each other up about we should have done this, we could have done that?
Yep.
Okay, move.
No, no.
I'm glad you brought
I'm
it
glad
in.
you did.
Hello, Paolo. Welcome to the Royal Society of Chemistry. There are lots of chemists here who want to know what other discoveries you may have made on this mission or intend to make other than just organic chemicals. Have you found significant amounts of inorganic chemicals that may be of use?
Unfortunately, you're talking to an engineer, and my knowledge of chemistry is really, really weak. Don't test me. The only important thing that I have managed to understand is that the rock where the Curiosity vehicle is parked and the sample that I extracted with the drill is phyllosilicates. That means that it is a rock that was formed in presence of water with neutral pH. If you go up to that point, we had found rocks formed in presence of water, but really acidic water. Something that you can find with isotope, for example. If you go and analyze those samples, you can probably find microscopic life, but not life. So finding that on Mars there was liquid water at neutral pH is.
Okay, gentleman over there. Get your hand up so they can find you.
So you send instructors in the morning for the day's driving. Does it then send constant messages back? You respond, or
No, as we don't see Mars all the time. In the same way, Mars doesn't see Earth all the time. So what we do is communicate only at specific times. We typically send commands directly to the vehicle, but then the results are sent to the orbiters. And the orbiters sends data to Earth only when they see Earth. And that happens on Curiosity typically once or twice.
does it stop? Gets a problem?
The vehicle, yes. The major part of my job is I try to define those commands that help the rover stop in case of trouble. So defining the commands on where to drive in half an hour, you're done. The remaining part is the big. It is try to protect the vehicle from having a bad day. The good thing of driving a vehicle on Mars from Los Angeles is that Tijuana, Mexico, it's just that Paul's. They don't have explanation.
So you effectively give it a list of errands to run, and then at the end of the day, you find out how it's done. What's the most surprised you've been at the end of the day to discover where Curiosity is compared to where you thought it was going to be?
Curiosity, she has followed up instructions pretty well. We had some interesting events with the past rovers. Well, for example, on these two events happened on Opportunity. One, we had told the vehicle to drive in one direction, then turn, and then we intended to drive forwards inside the vehicle and drive 20 meters forward. The next day we come in and the rover had driven 20 meters backwards.
Easy to get these things wrong. Now, there was another hand I saw right over there. Do you remember Paolo at the start, by the way, saying his pictures were particularly for any of the younger people who were here? So you need to start asking questions, young people, is all I'm saying.
Yes.
Hi, Paolo. Thank you very much for the talk. I wanted to ask, what about the instruments? Say they were to go funny, or they went out of calibration. How do you recalibrate them? Or if something to break, is there a way to...
Could you speak loud?
Yeah, sorry. What happens to the instrument if they go out of calibration? Are they automatically calibrated, or do you, how would that work?
That is a really good question, and nobody asked me. We have means to recalibrate the instruments, including science instruments. All of them have calibration targets. We have calibration targets for cameras. For the spectrometers, we have samples of known materials that have been installed on the vehicle, and we can either image them or we can place the instruments on those samples, so we can periodically make measurements to verify the calibration.
Okay. Not exactly fitting teenager image I was going for, if you don't mind me saying so, sir, but still, you've got the hand up.
Thank you. Could you describe the power plant facilities that you have on board? And my second question is, what happens if you have a flat tire?
Okay, so the power source for Curiosity is a radioisotope generator, which is made out of 4 plutonium pills, about like this tall and a couple of centimeters in diameter, being radioactive, and they become hot. We have transducers that transcode the heat into electric energy. We charge the batteries. The RTG is about 110 watts per hour, so we get about 2,600 watts per cell. Regarding the flat tires, the thread is about 20 sheets of print paper thick. And on Earth, since the gravity is 3 times higher than Mars, they get damaged quite a bit. So we typically have to replace those wheels every once in a while. Even we have driven with wheels with the thread completely torn apart. The cleats that we have on the wheels, they're still able to maintain the wheel in shape, and therefore we can drive along. If you take a look at the images that are available on the web, taking off the wheels, you can see that there are some things really on those wheels.
Just while we're on the wheels, you mentioned that from Sojourner to Spirit Opportunity to Curiosity, the wheels have roughly doubled in size, but you also talked about meetings and meetings and meetings. So whether they go back, it was like whether the whole meeting's about whether it was a millimetre bigger and a millimetre smaller. I mean, these things, everything is bespoke, isn't it? How do you decide exactly what size the wheel should be?
Because we know what type of terrain we were given specifications for the type of terrain that we wanted to drive on, the size of obstacles that now we want to drive on. Regarding wheels, there is a well-known story behind it, that the cleats that we had originally designed were spelling JPL. When NASA saw that, they said no. So we had to redesign wheels. So we installed an experiment to measure the compressibility of the plane, and therefore we installed holes. So the number of holes in wheels. The fact that those holes spell JPL is a good coincidence.
We're going to go there, and then there, and then we're going to go there.
Given you've got this sort of area in which the lander can land, and then you've only got a limited amount of drive distance, how much was where it actually landed as opposed to where you wanted it to land? Has that altered what you can do?
So we landed about 2 kilometers east and half a kilometer south where the center of the ellipse was. So we were quite close.
Okay, just on the other side.
You showed earlier the difference in computing power between 3 different rovers. I'm guessing from concept of the rover to the actual landing date is quite long. So at what stage do you think, with changes in technology, do you suddenly make a decision to go with a new camera or a new piece of analytical technology? Or do you have to stay with the original plan?
The design of the vehicle began in 2006, if I'm mistaken, but the construction began in 2008. So at that time, the iMac was not that old. The design decisions and changes, they take a long time because you don't want to, you cannot make a change at your subsystem, even if you're owner of that subsystem, because your change might affect the way that the vehicle behaves in the future by interacting with other components. So you need to get approval, and it's a really long process. So it's not that easy. You cannot just swap the lens, for example, or the cameras and put on 24 megapixel camera. Even because that is going to has a ripple effect. Suppose that you want to increase the resolution of the camera, you're going to reduce the number of pictures that you save storage. It's going to take much longer to take downlink that image. So as you can see, even this pre-serial is going to create a ripple effect that is really difficult to predict.
You've been waiting a while, sorry.
So on this planet, people write their name on walls with spray and create their name in wood. You use a laser on Mars. How long would, we can clean the walls, but nobody's going to clean what you use, laser on Mars. How long would that last, considering erosion, the holes that you're doing and the tracks that you're leaving when someone lands on Mars? Will they see the tracks?
So I haven't put my name on any rock on Mars. I think that I'm very lucky it would be the last thing that I would do on Mars. But I have drilled 4 holes on Mars. They will probably last more than 2 minutes. That is probably one of the most humbling things on Mars.
That sounds like a very good last question, but I just want to see if there's any more in the house. No, that seems like an almost natural point. But I've got one more from me, though. There is another Ray Bradbury story, which is just called Mars is Heaven. Do you think of this job as being not just the best job on Earth, but maybe the best job in the solar system, or is it one where you actually find yourself thinking, oh, another day driving that rover?
It was getting to that point. So, as I was saying, I'm in these lectures exactly to research. At least to me, this is the best job I could ever dream.
Okay. On that note, can we please one more time thank Paolo Bellutta? So that is where we officially bring this particular Martian Chronicle to an end, though. But Ray Bradbury also wrote Dandelion Wine. Don't have dandelion on offer, but as has already been mentioned by Robert, next door we do have some interesting, well, red, of course, for Mars, and some white too. So if you would like to go through to the council room, which is, I think, for one night only in the Mars bar, you can go. Thank you very much indeed. And I also thank Edwin and everybody from the RSC for organising tonight, yourselves for coming along, anybody watching the webcast, and particularly those of you in the upper left. Thank you for being here. Oh, and just to make a complete end of it, and please fill in your feedback forms. Remember, there's 1 L in marvellous. Gale Crater.